Oh, hey physics fans, how's it going? Today we're going to be talking about Ampere's law. So what Ampere's law describes is the relationship between the magnetic field around a path integral to the enclosed current by that magnetic field. So if we go ahead and break that equation down, we're going to have a enclosed path integral where we're taking the dot product between the magnetic field vector and the differential length vector. Then that is going to be equivalent to the permeability of free space multiplied by the enclosed current inside of our loop. So essentially you'll notice that this side of this equation is a scalar quantity. We just have our enclosed current, and this permeability of free space is a constant that's available on the PRC. So this side is a scalar, and you'll notice that this other side is two vectors with a dot product. We are taking the integral of it, but that whole thing is still going to become a scalar once we evaluate it. So this works out to be a scalar on either side of the equation. Now, to take a look at an example of that, we're going to consider a long straight current carrying wire. So if we have our wire located here and it is carrying current out of the screen toward you, then we're going to be basically considering this blue ring as our path integral. It's closed, it goes all the way around in a loop. If we consider any given point on that location, we're going to have a magnetic field created at that location, and we're going to have our differential vector. So that differential vector just has a normal small differential length, but because it's a vector, it points along the direction that we're considering the path. Considering the dot product between these two quantities, because they are always going to be pointing in the same direction because of the right-hand rule for creating magnetic fields, we can see that this angle here is always going to be equal to 0, which means the cosine of that angle is going to be 1. So we can evaluate it just as the magnitude of these two quantities. Once we plug that into an integral, this differential length is going to become our full circumference, so 2 pi times our radius r. And we can then evaluate that to get this equation which appears on your PRC. This one is describing the magnetic field, the magnitude of a magnetic field created a distance r away from a current carrying wire, which is carrying a current of I, and has the permeability of free space from your PRC. So that is one of the equations that you'll see there. There are a number of other ones for other situations. If you have more questions about those, you can ask your instructor or check out the notes inside your book. And let's get over to a problem. All right, now let's do a practice problem. So we're going to do problem 12-24 out of your books. Reading through that problem, we find that we're going to be calculating the magnetic fields created by two different current carrying wires. What we want to determine is the net magnetic field that is going to be created at a particular point by those two wires. To do that, the physics step that we'll be using is going to be the magnitude of a magnetic field created by a long straight current carrying wire, which is given by the permittivity of free space times the current divided by 2 pi times the radius or distance away you are from the wire. The draw step here is the same figure that appears inside your book. We have our top wire, which is carrying current in this direction here. We'll call that wire 1. We have our bottom wire, which is carrying current in the same direction, call that wire 2. And the two different points we're considering for part A and B are P1 and P2. The givens that we have, we're solving this algebraically, is going to be I for the current carried inside each of the wires, and A is this base distance that we'll be using when we plug in values for the different distances. The assumptions that we'll be making are that we are using a long straight current carrying wires for both of the two wires we're considering. So, moving on to our solve step, we have the net magnetic field is equal to B1 plus B2, where these are each the two components that we're considering, and they have to be added together as vectors. I've written down what the magnitude of each of those would be, created from this equation here, where we're now considering plugging in values for the current for each value and for the distance away they are. For part A, as we consider them, we'll find that the distance away for each one from P1 is going to be a value A, and they have the same currents, so the magnitude for each of these is going to be the same. Their directions, however, are going to be different. The directions for the magnetic field created by a current carrying wire are determined using a right-hand rule. What you do is you take your thumb and you point it in the direction that the current is pointing in, and then you're going to curl your fingers around that wire. And the tips of your fingers the whole time point in the direction of the magnetic field created. So in this case, if I point my thumb in the direction of I, I'm going to curl it and find that my fingers are pointing into the screen at point P1. On the bottom one, as I curl it, I'm going to find that my fingers are pointing out of the screen. If we call into the screen negative k direction and out of the screen positive k direction, we're then going to get these values for b1 and b2 for their vectors. Plugging those into those equations, because they're in opposite directions and have the same magnitude, we get a net magnetic field at location p1 of 0. For part B, we have the same base equations for the magnitudes of b1 and b2. However, the distances away for each one are now going to be bigger, because for 2 it's 2a, and for 1 it is now 4a away. So that gives our different values for each magnitude. In terms of direction, now we have both of them pointing into the screen, which means they're both going to be pointing in the negative k direction. Plugging those in, we then get a sum that's equal to -3 times the permeability of free space times the current, divided by 8 times pi times the distance value a, all in the k hat in the negative k hat direction. Moving on to our check step, we didn't have to use units, and we didn't have to use sig figs because we have algebraic solutions. It does look reasonable because we have a balanced set of fields at our point in between the two of them, and then we have them both adding together algebraically for the second location. So that's it for this problem. If you have any more questions about this material, check with your instructor, and you get a little more background about the historical value of Ampere's law. Thank you. We'll see you again. Who needs an eraser?